Hello, Mastertron Tamer here. Today we're going to take a look at the evolution and the inner workings of file formats that are currently in use. The first major file format that was used in the big data space is something called the sequence file. The sequence file had been created by Doug Cutting, the creator of Hadoop, and he was looking for a file that would be very fast for the distributed computing model that they were using. So what I've illustrated here is, think of this box. It could be a block of data if we were talking about the Hadoop file system where data is cut up into blocks of 128 megs. But let's just think of it as a file. So this could represent our file. So what was a sequence file? Well, it was a key value store. Now, one interesting thing about this key value store was the data types that Doug used when he created this were unique. They were unique to the sequence file and to the Hadoop ecosystem. So while this file was great for processing, it was very fast because he had created data types that were very light on their feet. None of the bloat that we would have, say, with Java data types. But it was tightly coupled to the Hadoop ecosystem. That made it difficult to read outside of that system. Now you can read it outside of that system, but it was difficult. There was an open API for doing that, but it was a lot of extra work. So what they really needed was a file system that was like this, a binary key value store, which is what sequence files were, but yet were not tightly coupled to Hadoop. So Doug got together with some of his programming buddies, and this was even easier to do because at the time he was chairman of the Apache Software Foundation, and said, we need to solve this problem. We need to come up with a universal file format that is binary, which is concise, and which will be good to take to other systems. So to solve this problem, one of the things they did is they said, hey, let's put a header on top of the file. Now that we've got a header on top of the file, we can put in there the information that's going to define these data types. That's great. That'll make the file much more transportable. But the next piece of that is that we need to have a data type that we can all agree on. So the solution they came up with, you're going to like this one, was to use JSON. JSON was an established standard at the time, and this would make it easy to move around because everybody understood JSON. It had the added advantage that the JSON header information would be in plain text. You could take the header of this file into any text editor and just read about the data types. So it was not difficult to work with at all. So the name of this file format is Avro, and you probably have heard of it, I would assume. This is the actual logo if you've never seen it before. I think it's like Red Bull. It gives your file wings so that it can be transportable. The actual logo, though, is a throwback to an aviation company, I think from the 60s. But anyways, I digress. Avro became an important standard right away, within about 6 months, I would say. At the time, we had estimated that 50% of the data had already migrated from sequence files to Avro. It was that great of a change. One of the reasons this happened is it turned out to be a great file format for putting your data to rest, and there was no penalty when you brought it back to process it because of the way it was laid out so efficiently, and it was transportable. We lost the problem of being tightly coupled to Hadoop like the sequence file had. So almost everything was perfect with this file format, to be quite honest, and it's still used today. The one downside to Avro was it wasn't really engineered as a columnar file store. And what I mean by that is if we were in the situation where you needed to read in columns of data, let's say each record had 100 columns, and you were just doing analysis on 2 of them, with the Avro format, we would have to read in the full record, the whole 100 columns, and then parse out the ones we want. So this was an issue with performance. Representing columns of data is no problem in Avro because the data types of both the key and the value can be complex data types. So representing it was not an issue, but performance specifically with columnar data and when you were doing analysis on just a few of the columns was an issue. So what was needed was a universal columnar format. And let's talk a little bit about that. The concept is very much the same. We're going to start with a file here, right? But rather than organizing like we would typically with a key value store, we're going to organize the data by column. So what we'll do is we'll put all the data of column A in one block, and then we'll record the offset to where the column B data starts, and then there'll be all the column B data, and the same for the column C data and the column D data. And now let's visualize this. Let's say, this is a simple one, but let's say that what we've got in here are team scores. So the A column holds the name of the first team. The B column holds the name of the second team. Let's say C holds the date that they had the game. And D holds the score. But for our analysis, what we want to do is just get an average of the scores. We don't care about A, B, or C. With a columnar format, we can go straight to the beginning of D and just retrieve that data with the scores in it, thus conceivably moving only a quarter of the data across. So this is the big benefit of a columnar file store. We see the most advantage to a columnar file store when we have lots of columns in our data set, but we routinely do analysis on just a few of them. These subblocks of data are sometimes referred to as columnar groups. In fact, that's what I learned to call them. Lately, people have kind of settled on calling them column chunks. This idea of columnar file formats comes into the big data space as a sort of solution for some of the speed issues with Hive. And if you're unfamiliar with Hive, it's the original SQL on Hadoop solution, which basically took your SQL query and turned it into Java MapReduce. It was great because that opened up a whole host of new people who could use this system because there were so many people who knew SQL. But the downside to this is you give people a SQL tool and they're going to expect SQL-like performance. Hive just was never going to be there because it's sitting, at least originally, was sitting on top of MapReduce. So coming up with columnar file formats was one way to improve its performance. And there's actually been a few of these that have come up through with the same goal. The first one was kind of a text-based one, and that wasn't honestly a great improvement because of that. Then we started getting into binary solutions, and they were better yet. But we ran into still this issue of transportability. Now we are tightly coupled to the Hadoop ecosystem, and we're tightly coupled to Hive. So we really needed something that was universal. So in trying to solve this problem of having a binary column or file format for speed, but yet that everybody could use, the solution is going to seem a little bit familiar to you. We're going to splice on a header, which is going to hold the metadata. But the real question is what do we want to use as our standard for that header? So we got a bit of luck at this point as they were working on this project. There were several different kind of formats that were proposed. Actually, Doug Cutting had come up with another one that was going to give us the columnar benefits. But again, we wanted a universal standard for this. So the bit of luck that they had at this point was the fact that at Google, they had a project called Dremel. And what it was a high-speed query engine to use internally at Google. Now, Google never opened this up for everybody to use. However, they were nice enough to publish this great paper about how Dremel works. This particular paper has been kind of a seeding ground for a whole bunch of projects, actually. You may have heard of Drill or Impala or Dremio. All of those projects can trace their origin back to this one paper. But there's one more thing that comes out of this paper, and that is that in it they describe a file format for the same high-speed query work that they were doing. So what they did is they said, why don't we use that as the template? Effectively, Google's put a lot of research into this. Why don't we base our file format on what they have come up with already? So, going back, they said, we'll use this file format standard that Google had already come up with. Engineers from at the time from Twitter and Cloudera got together and said, let's make it an open source project based on this same design. Now they knew kind of how they would organize it, how the metadata would work, and this project became Parquet. So Parquet, if we want to think about it, is a binary record columnar format that combines the benefits of columnar block storage so that we can find data of just the columns we're after. It also carries metadata with it, and now the file is completely transportable. This file format has been particularly important for Spark processing, primarily because the data frame abstraction that's used in Spark is itself a hybrid of metadata and an RDD full of row objects. Don't have to worry too much about that. If you want more detail on that, I'm going to be doing a video later that explains that. But there was kind of a need in the Spark ecosystem to marry the metadata and the actual data together in a file format and be a fast SQL file format. So Parquet kind of presented itself as the perfect solution. I hope you've appreciated this little walk through the file systems of big data and cloud storage. These days, Parquet is basically the number one out there that's being used. Avro is still used, but Parquet has the use case where we have lots of columns in our data, then we're going to get our best performance out of Parquet. Again, hope you enjoyed it. And if you feel like this has been of any value to you, please go ahead, hit that subscribe button, and hopefully we'll be together on another video.